So my talk today is about code quality and whether that actually matters in a data science setting. And code quality is quite a subjective topic in software engineering, and there are many very opinionated tomes out there that you can read on this subject. But data science itself is quite a... it's not particularly well defined as a approach, as a tool set and things like that. So this is a subjective thing about a moving target. So everything I say today, take everything with a pinch of salt. You may have completely different opinions, and that's fine. The point of this is to kind of, discuss what looks like good code and what doesn't in a typical project. So me, yes, I'm Russ. I started working at Jumping Rivers a couple of years ago, and I do various things online for our communities and stuff like that. Okay, so code quality. So I got this picture from a book by Tom Long. You might not be able to read the stuff at the bottom. It's called Good Code, Bad Code, the book. And in it, he describes two separate kind of viewpoints of code quality. So there's the bit on the left-hand side here, which are the kind of aims of what it is about good code that means that it's, likely to last the test of time. So that it works, so for a given project that it works, that it keeps working, that you've got things in place to ensure that the code you've written today will continue to work as a project evolves. That it's adaptable and it doesn't reinvent the wheel, because you don't want to be, writing more than you actually need to. But they're the goals of code quality. But how you actually achieve that is from the stuff on the right-hand side. In an ideal world, the code that you write should be, understandable by someone reading it. That it should do precisely what it describes that it does. And it should be hard to misuse. But also, it's important to kind of structure your code appropriately so that it can be reused and things. So modularity and generalizability are quite important. Something that's quite close to my heart is that code should be testable. Not quite so much that code should be tested, but testable code is exceptionally important because it helps build the rest of that stack of things there. When does it matter, though? So when does it matter that your code can be understandable and kind of do what it says that it does? It principally matters when you're working with multiple people and when you're trying to take maybe your project that you've been working on your desktop and deliver it to the world. Maybe you have to interact with software engineers who aren't of your analytical kind of frame of mind, statistical frame of mind. And yeah, there's a few other settings when it matters. And for me, for this talk today, the key ingredient here is that the code that you write today, you should try and write it in such a way that in the future, if you come back to it, you understand what it does. Yes, I've seen a lot of code quality talks, and they usually have a religious zeal, and I don't want that to be the talk that we do today. And I'm actually going to show you a project that I've been working on. Well, I've not really been working on for 4 years, but okay. So the project. So what this repo described up there is. 4 years ago, as a bioinformatician, I was working at the University of Glasgow, and I wanted to do something different. And at the time, I was working on lintar, and I was writing other packages for myself and things like that. And I wanted to do more kind of general software-y stuff. This project I just kind of put together as a way to show something that wasn't clinical bioinformatics type stuff. And all it does is it analyzes code in a bunch of R packages. The R packages all relate to like software development. And I got them from you know, like the CRAN task views thing. There was a software development one at the time. So it analyzes things like the lines of code in there, you know, how big the functions are. It analyzes the kind of social history of the repository, who contributes to what, who touches which files and things. And because I was writing a package at the time, I have a package called Dupree that kind of finds duplicated code in R projects. I was quite interested to see how much of that. We're not going to talk about any of the results from it. We're going to talk about the code itself today. So the first of those code quality goals was that something works, and it doesn't work. 4 years later, you know, I'd written this with what I considered to be, you know, best practices at the time. There was a Conda environment that defined where the project ran. The data that it was based on was kind of configurable and things like that. And it had kind of workflow management and all this kind of bells and whistles. But it doesn't actually work now. So to fit in with this talk, I kind of wanted to work out how much graft would be involved to get that project working again, to make it such that we can extend it and to reuse the components within it. And it was a surprising lot for something that I thought at the time I'd written pretty well. The project structure looks like this. So the most important thing in there is the scripts directory. Each of those scripts is like a .r file, but which is ran as a command line script. And when I was writing the abstract for this, I was considering putting something together along the lines of in praise of the script, because I think the R Markdown world and stuff have kind of made R as a scripting language a bit less of a selling point, but it's great. So they're all scripts. There's a run, like a bash script that runs the whole thing. There's a workflow manager to make sure that you don't duplicate the amount of work that gets done. You might not know any of the tools that are involved in this project, but the SnakeMate, which is used in Conda, were prevalent across bioinformatics at the time and probably still are. Anyway, a typical script looks like this. We've got a bunch of functions in there and some tests for those functions and a way of defining command line arguments. And then at the end of the script, there's something that basically just runs the content of those scripts. These scripts are written in a way such they can't be sourced into a running R session. So these are quite different from how you might typically write R code, where you might source a file in or load a package and then use the code within it. These are designed to be ran on their own, but what that means is they're not really reusable. Any of the functions that I write in here can't be reused if I want to, use them again in something else. The tests aren't great. So I had tests just to check that things were working as I was kind of developing stuff, but I didn't have like a kind of, CI setup or anything like that to make sure that they run and things like that. So, there was some good stuff and there was some bad stuff. Right. So it doesn't work. So I fixed the code and things like that. There were various things that I needed to do, get the environments working and get the URLs sorted so that it pointed to the right set of packages that I wanted to analyze. The second of those goals of code quality that your code keeps working. And that's kind of keeping working under changes to things like data, changes to things like, you know, as packages evolve, I mean, the packages, the runtime packages that the project depends upon. That this is a project that analyzes packages might cause some confusion. But, and key to that, for me, is testing. So there's a lot of stuff that can shift under an analysis project. There are ways to ensure that, you know, your projects keep running that I hadn't got in place. I could have done CI things and stuff like that, but I didn't, because it was just a kind of one-off project. But anyway, yes, all of these things failed. But anyway, we're going to talk about testing. So this is an example function from one of those projects, right? What this does is it analyzes the Git commit history of a repository. Gitsum, the package, was written by someone else. And what it does is it takes a repository defined by a path and creates a kind of log of the changes to that repository that is then stored inside the repository. Then, in order to use that within R, we have to read that log back in using parse log detailed, and then we do a little bit of kind of, you know, dplyr type, data manipulation type stuff. Okay, so that's a function, and in one of the scripts, you'd do something like this. So you'd call that function, and then write whatever your analysis results are out to a file. Right. That function in this particular script is untested, and it's hard to test. And it's probably poorly named. Some of the arguments were weirdly named as well. And so it's nested inside a script that can't then be used in other projects. So it's modular, but it's not reusable. Right, so I wasn't intending to show you what an exceptionally good project should look like. I wanted to show you something that could be improved. Right. This book, Grokking Simplicity, is, if you've not done much functional programming before, if the world of Perl and such like ground that you've yet to break, this is a wonderful book for explaining the fundamentals, the kind of mindset of functional programming. It does talk about things that we are kind of saved from in R, about data mutability and stuff like that, which aren't a huge issue for us as R programmers. But one of the best things in this book is that it describes a way to kind of partition the different processes in a software project up into data, which is kind of fixed and kind of unchanging, calculations, and actions. Now, it's quite an important distinction, this. A calculation is something that just converts some input to an output. It does nothing. It has no side effects. It doesn't depend on any external additional stuff that might mean that when it runs on one day, it gives you a different result to run on another day. If you provide it the same data, it should always give you the same output. Whereas an action is something that might have side effects, like writing to a file or depending on the random number generator or something like that. Calculations are far easier to test than actions, because you can set up some data, use that data, and it should return exactly the same value each time you call that function. So these are perfectly easy to test. Actions, you have to set up a load of additional stuff, mocks and kind of example files and things like that. So if we go back to that function, what I've done here is annotate which of the different steps in these functions are actions with an A, and which are calculations. So init.gitsum adds that log file to a repository. Parse log reads in that log file. So they're both actions. They touch the file system. All these subsequent things are kind of formatting that data. So they, you know, that's a pure function. It converts the same unnest log. If you gave it the same log, it would give you the same output. So it's important to kind of think about what kind of process is going on in my different bits. Sorry. And then the updated version. What I did was I rewrote this to make it easier to test the bits that I'd written. Here we go. So what I've done here is I pulled out all that formatting logic into a new function. And as you can see here, everything inside there is a calculation. We're, you know, expanding that the data into a big file, and then like not into a file. Changing some data in there, formatting and filtering and things like that. They're all calculations. Everything at the top, though, there's some actions and some calculations. The difference between an action and a calculation that's important here is that if you've written a function and it calls something that is an action, then that function you've written becomes an action. It becomes harder to test and things like that. This here is extremely easy to test now. So when you're, when you're writing test code to ensure that your code continues to be usable, it's useful to kind of think about the types of processes that are going on. The third goal was that it's adaptable. So if I wanted to change some aspect of this project, if I wanted to analyze, the packages related to time series analysis or something like that, what would I need to change in the project to make that work? And there's lots of things. And so how do you write your code so that it's adaptable? There's a few different ways that you can do this, right? So if we pick a kind of example function, here we've got a function where we've hard-coded a value inside the body of that function. So this is some file path, some URL, that's hard-coded into that function. So as a user of that, you can't modify the file that it uses. And what you find yourself doing, if you need to evolve the project such that it uses a different URL, or maybe that changes or something like that, you tweak the body inside that function. And that's that should set off red flags in your head. Because if you need to tweak that body to evolve a project for reasons that aren't just like, logic changes and stuff like that, maybe that should be an argument, or maybe it should be stored in an object that you pass in, or something like that. And there's similar things that you can do with a script, but I'll zip past that. The final goal, so the aim is to write your functions so that they're adaptable. And then finally, it doesn't reinvent the wheel. Within a project, you'll write lots of code. Someone was saying earlier on that they have a project workflow that they're wanting to split up into, extract the duplicated code into packages and things like that. And how do we actually do this, though? So there's one rule of thumb that kind of comes through really nicely here, which is if you write the same code 3 times, you should refactor that code into a function or a more general function, something like that. But the only problem with that is you might not realize that you've written the code 3 times. Because code can look different from one day to the next. And unless you've just copied and pasted explicitly, it might not be obvious that they've wrote the same code. And particularly if you're doing it across different projects. So I have a package called Dupree, which will take either a directory or a package structure or something like that, and find duplicated code within it. So if you find 3 chunks of code within a file or within a directory or something like that, maybe that's something that you could generalize and bring out into something else. These little steps, they won't help your project on the day that it's initialized, but they're important for the kind of long-term health of your project. So do those code quality books really matter to us in data science? How is it really different? There's more of an exploratory phase. The group's typically smaller than software engineering generally, and we have different training. So a lot of the kind of sensibilities that come into software engineering may not be embedded with us. But I do think it's important that we think about these things, especially if working across larger groups and with other individuals. So that's my talk. Thank you ever so much.